Hi, and thank you for tuning in to this screening tutorial. Today we are going to be interpreting a question, setting up a 2x2 table, and then from that information calculating sensitivity, specificity, positive predictive value, negative predictive value, and prevalence. So the question asks, in a study of 100,000 women, 100 are known to have breast cancer. Of these, 90 had an abnormal mammogram. Of the 99,900 women without breast cancer, 94,905 had a normal mammogram. So what we want to do is we want to first set up our 2x2 table with the information that we have. So let's go ahead and set that up. Let me change that to a finer point here. Okay, so let's go ahead and set up our 2x2 table. And on the top here we're going to have breast cancer, positive, negative, and then we're going to have here mammogram, and we're going to say positive is abnormal and negative is normal. So looking at the information we have here, we have 100,000 women total, so we can put that information right here. And then 100 are known to have breast cancer. So if they have breast cancer, that's going to go in this section here, positive. They have breast cancer. So we'll put 100 here. Of these 100 women, 90 had an abnormal mammogram. So we know that 90 tested positive, essentially. So then we can infer that we have 10 who have breast cancer and had a normal mammogram. Next, what we want to do is take the 99,900 women without breast cancer, and we'll put that here. And 94,905 of those women had a normal mammogram, so we'll put that number here. And then if we take the result of these two numbers, minusing 94,905 from 99,900, we have 4,995 here. And then I like to put out to the side the sum of these two numbers, so 5,085 and 94,915. That way I can check my work and make sure everything adds up. So what we want to do first is we want to, let's go ahead and calculate our prevalence. So our prevalence formula is going to be 100 over 100,000. So these are prevalent cases, and this is the population. And that is going to give us 0.001 times that by 100, and the prevalence is 0.1%. Okay, so taking the information from the last slide, we have our 2x2 table, and then we have our prevalence calculated here. So next we want to calculate our sensitivity, and I'll just put SENS for sensitivity, and that is going to be A over A plus C. Now, let's go ahead and, at this time, put some labels on our table here. So we're going to say A, B, C, and D. So A is 90 divided by A plus C, so that's 90 plus 10, and this is going to give us 0.9, and then we'll times that by 100, and that gives us 90%. So the sensitivity is 90%, and to interpret that, you're going to say, of those who have breast cancer, 90% will test positive. Next, we're going to calculate our specificity, and that is going to be D over B plus D. So that's going to be our cases here, our women who don't have breast cancer and also have a normal mammogram, divided by all women without breast cancer. So that's going to be 94,905 divided by the sum of B plus D, so 4,995 plus 94,905. And that's going to give us 0.95 times 100 equals 95%. And to interpret this, you would say, of those, or women, who don't have breast cancer, 95% will test negative. Next, we want to do our positive predictive value, or PPV, and that's going to be A over A plus B. So now we're working our way across here, whereas before we were working down. So that's going to be 90 over 90 plus 4,995. So these are women with breast cancer who tested or who had an abnormal mammogram out of all of the women who had an abnormal mammogram. And that number here is going to give us 11504. Go ahead and times that by 100, and rounding appropriately, we get 1.77%. And then to interpret this, we would say, of those who test positive or have an abnormal mammogram, 1.77% actually have breast cancer. And then we will do our negative predictive value, or NPV, and that's going to be D divided by C plus D. So that's going to be 10 divided by 10 plus 94,905. So these are women who have breast cancer but have a normal mammogram out of all of the women who have a who have a normal mammogram. So if we calculate that, we get 0.9998946, and it goes on. Go ahead and times that by 100. And we get 99.989%. And to interpret that, you would say, of those who test negative or have a normal mammogram, 99.989% actually do not have breast cancer. So now we want to take this same information, but we want to apply it to a different population. And in this population, let's say that 0.5% of the population has breast cancer. And we have a population of 100,000. Let's also assume that the sensitivity is 90%, just like the last example, and the specificity is 95%, just like the last example. So with this information, we have our sensitivity, we know is 90%. We have our specificity, which is 95%. And then we need to put together a 2x2 table and figure out our positive predictive value, or the PPV. So let's draw our 2x2 table. And put in our labels. So breast cancer, positive, negative, mammogram, abnormal, and normal. And then we'll go ahead and put our labels here as well. And we know we have a population of 100,000, and that our prevalence is 0.5%. So first, let's find out how many women have breast cancer. So we have 100,000 times 0.5%, and that's going to give us 500. So we can put 500 right here. From this, we can calculate how many women don't have breast cancer, which is 100,000 minus 500. So we can put that number right here. Next, we can start filling in the rest of this table. So sensitivity is equal to A divided by A plus C, and we know that our sensitivity equals 0.90. And we also know that A plus C is equal to 500. So we'll just times by 500 here, times by 500 here, and A equals 450. So now we can plug that in here on our table, And then we can get C by subtracting 450 from 500. So that's 50. Next, we know that our specificity is 95%. And we also know that that formula is D divided by B plus D. We know that B plus D is equal to 99,500. So let's times this by 99,500, times this by 99,500, and D equals 94,525. So we can put that in here. And then subtract that number from 99,500, and we get 44,975. So now what we want to do is calculate our positive predictive value. And that formula is A over A plus B. So that's 450 divided by 450 plus 4,975, which equals 0.082949 and it goes on. We'll times that by 100, and we get 8.29% as our positive predictive value. So with a new prevalence of 0.5%, our new positive predictive value is 8.29%. Now, if you remember from the last slide, our positive predictive value was 1.77%, and the prevalence was 0.1%. With the higher prevalence of 0.5%, our positive predictive value also increases. So you know that if you have higher prevalence in a population, you will have a higher positive predictive value. I hope this information was helpful, and please feel free to ask any questions. Thank you so much.